Hi. Now, I've got a question here on connected particles that you might like to try. What I've done though is the question starts from here, in fact, so it's this section that you should read first and then go on to the questions up the top here, because I'm going to be removing this part to give me space to do the work solution. So let's just read through the question first of all. And what we've got here then is that the figure shows two particles, A and B, of masses 2m and 4m respectively, connected by a light inextensible string. Initially, A is held at rest on a rough inclined plane which is fixed to horizontal ground. The plane is inclined to the horizontal at an angle alpha, where tan alpha equals 3/4. The coefficient of friction between A and the plane is 1/4. And we're told that the strings pass over a small smooth pulley P, which is fixed at the top of the plane. And the part of the string from A to P is parallel to the line of greatest slope of the plane, and B hangs vertically below P. The system is released from rest with the string taut, with A at the point X and B at a height H above the ground. And what we've got to do for the motion until B hits the ground, that is, we've got to work out in part A to give a reason why the magnitudes of the accelerations of the two particles are the same, and in part B we've got to write down an equation of motion for each particle, and in part C find the acceleration of each particle. Okay, well let's just see how you got on if you did have a go at this. Well, for part A we've got to give a reason then why the magnitudes of the accelerations of the two particles are the same. Well, that's on this fact here, that the string is inextensible, that is, it doesn't stretch. So as soon as particle B starts to move down, A will start to move immediately up the plane. So they're going to move with the same acceleration purely because the string is inextensible. So we'll just write that in it there. The string is inextensible. Right, okay, so that's part A. Now I'm going to need room to do all the other parts to this question, so I'm going to remove this. But what we'll need to remember is that tan of alpha equals 3/4 and the coefficient of friction between A and the plane is 1/4. So what I'll do is we'll just remove the question, and we'll also remove just this introduction that was up there, and we'll just recap that we're told that the coefficient of friction, that's mu, equals 1/4, and we're also told that tan alpha equals 3/4. And for that, what I'm going to do is just draw a small right angle triangle here with alpha, and it's a right angle triangle, so because the tan of alpha is 3/4, tan of an angle compares the opposite side to the adjacent side, so that's why I've written the 3 and the 4 there. And by Pythagoras' theorem you'd find that the hypotenuse was 5 units. And this gives us our ratios that we'll use later on for things like the cosine of alpha, which is adjacent over hypotenuse, 4/5, and the sine of alpha, which is opposite over hypotenuse, 3/5. We have no need to work out what the angle alpha is. So for part B we've got to write down an equation of motion for each particle. Now before we can ever get to that, that's by the way is applying Newton's second law, force equals mass times acceleration. But before we can ever do this we need to spend time marking out forces and angles on our diagram. So let's start with the forces first of all. If we turn our attention to particle A, we've got the weight of the particle. It's got a mass here of 2m, so its weight is going to be 2 mg newtons. We've also got the contact force, the normal contact force from the plane, so we'll mark that in as, say, R newtons. There's also the tension pulling it up the plane. As B moves down, A goes up the plane. And so we'll put a tension in there, call it T newtons. Okay, so that's T newtons. And because it's moving up this plane, which is rough, there's going to be friction that opposes motion. So it's going to be down the plane. Okay, and because it has reached its maximum, its limiting friction, that frictional force will be equal to mu times the normal contact force, mu r. So mu is a quarter, so we can say that this is going to be a quarter r newtons. Okay? Now, if we turn our attention to particle B, then the force is on this because it's moving downwards. Okay, it's going to be its weight. That would be its mass, which is 4m, multiplied by g, the acceleration due to gravity, and that would be measured in newtons. And we've also got a tension trying to slow it down from falling, okay, offering a resistance to motion. And that tension is in fact going to be exactly the same as the tension here. And that's because we're told in the question that this was a smooth pulley. So whenever you get smooth pulleys, the tensions are always going to be the same. So we'll call that T newtons there as well. Okay, we'll just pop that in up there, T newtons. Now, we've also got to mark on the accelerations, and we know that the accelerations of each particle are exactly the same because the string is inextensible, it doesn't stretch. So if B accelerates downwards, we'll do that with a double arrow and we'll call it A meters per second. Then particle A moves up the plane, it accelerates up the plane with the same acceleration. So I'll just call that A. I'll leave out the units because I haven't got much room there to put it in. Okay, so we've done that. Another thing that we should do now is put on the angles, okay? And when you're dealing with inclined planes, always put a dotted line, or a line anyway, in there. And we should know by now that this angle here is exactly the same as the angle of the plane. So this angle in here is going to be angle alpha. Okay, well, I think we've got everything that we need now for the diagram. That's the bit that generally takes the time. Now when it comes to writing down the equation of motion for each particle, let's start with particle B. I feel that's the easiest to work with. So we'll just put up here, we're on part B now, and I'm going to consider the motion of particle B. So we're applying Newton's second law, force equals mass times acceleration. And when something is moving and we look at applying that rule, do resolve in the direction of motion. So in other words, downwards is going to be taken as positive. Alright? So what we have now for the overall force, the resultant force acting on B, we've got all of 4mg, the weight acting downwards, so we've got 4mg minus the tension acting upwards. It's minus because T acts in the opposite sense to this. So this is the resultant force on B, and that resultant force is equal to mass times acceleration. The mass is 4m, and the acceleration is A. Alright? So there's our equation of motion for particle B. I'll number this equation number 1. We'll return to this later on. Okay, now we need to get an equation of motion for the other particle, particle A. So let's just say that we're considering particle A at this stage. Okay, I feel you ought to put some subtitle here so the reader knows which particle we're referring to. Now for this, you can see that the motion of A is up the plane. So what I want to do is resolve now up the plane. So if we resolve up the plane, taking up the plane as positive, then what I've got is all of T acts up the plane, so we've got T. and then we've got the frictional force. All the frictional force acts down the plane opposing that motion, okay? So it's going to be in the negative sense. So we've got minus a quarter times R, the normal contact force. Now, if I was to consider R, well, this reaction is perpendicular to the direction that we're resolving in, parallel to the plane. So therefore, any perpendicular forces have no effect in the equation here, in the motion. So I can neglect all of R there. That leaves us with the final force, the weight of the particle A. And you'll notice that this force is neither perpendicular to the direction that we're resolving or along the plane. It's inclined to the direction we're resolving. So we need to split it into two components. And we've got a right angle here, okay, so those two components will be one into the plane and one down the slope of the plane. The one into the plane would be 2mg cos alpha because it contains the angle alpha, 2mg cos alpha. But we don't use this one purely because it's perpendicular to the direction that we're resolving in. We want the one down the plane, and that component is going to be 2mg sine alpha because it excludes the angle here in this interval here, okay? So 2mg sine alpha, and it's going to be negative. So that's the component of the weight down the plane. And I'm assuming that you're familiar with splitting forces into components. If not, just check out splitting a force into components on my website. Okay? So this is the overall force acting on A, and this resultant force is equal to the mass times the acceleration. And the mass is 2m, and the acceleration is A. So that's our second equation of motion. We'll number that number 2. Okay? Now, as far as I can see, that is essentially part B done. Now for part C, we've got to find the acceleration of each particle. And in order to do that, what I'm going to do now is, well, we're going to need to work out what R is if we're to find out what A is in these equations. So I can get R by still working with particle A, but resolving perpendicular to the plane. So that's the next move that I'm going to make, resolving away from the plane, okay, taking that as positive. And if I do that, what we've got is all of R acts away from the plane, so we've got R. And then as for T and the friction, these two forces are perpendicular to this direction that we're resolving in. So I don't need to use T or the frictional force down the plane. But when it comes to the weight again, that is inclined to this direction. It's not perpendicular to this direction. So we split this into two components. One will be into the plane, one down the plane. The one down the plane, though, is now perpendicular to our direction. So we don't need to consider that one. We just need to consider the one into the plane. And it contains the angle here, alpha, so it's cosine of alpha that's used. 2mg cos alpha. And it's in the opposite direction to what I've selected here as being positive. So it's minus 2mg cosine or cos alpha. Now this is the resultant force on A, but in this perpendicular direction there's no acceleration. It's neither leaving the plane or moving into the plane. It's in relative equilibrium in this direction. So that resultant force must equal 0. And so from this equation we can see that if I add 2mg cos alpha to both sides, I therefore have R equals 2mg cos alpha. Okay? And if we just carry this on down here, let's just move this over, give us some space through here though. Okay, I can tidy this up because we now know that cos alpha is 4/5 adjacent over hypotenuse. So therefore r is going to equal 2mg multiplied by 4/5. And if we work that out, that's going to be 8/5 mg. Okay, so we've got that result there. Let's call this result number 3. So all I need to do now is substitute equation 3 into equation 2. So if we just say that here, sub 3 into 2, okay, then what do we get? Well, we've got t then, so therefore t minus 1/4 times r is 8/5 mg, and then we've got minus 2mg, and then it says sine alpha. Let's take the opportunity of writing sine alpha in as opposite over hypotenuse, which is 3/5, okay, and this equals 2ma, so equals 2ma. Now if we clean this up, I can see that that 4 goes into the 8 twice. So what we have then is t, and we've got minus 2/5 mg minus 6/5 mg, so it's going to be minus 8/5 mg is equal to 2ma. Now if I call this equation, say equation 4, now I can see that if we now combine this equation with equation 1 by adding 1 with 4, minus t and t are going to get cancelled out. It's going to give us 0. So we'll do equation 1 then plus equation 4. So what does that give us? Well, we've got 4mg here minus 8/5 mg. Well, 4mg in fifths is 20/5 minus 8/5, that's going to be 12/5. So we've got 12/5 mg, okay, equals, and then here we've got 4ma plus 2ma, so it's going to be equaling 6ma. And I can see that the m's cancel one another out, they're in both terms here. And so I've just got to divide by 6 to both sides, and that will give me the acceleration. So therefore the acceleration will be 12/5 divided by 6 is going to be 2/5, and we've got 2/5 g. If you take g though to be 9.8 meters per second, the acceleration due to gravity, 2/5 of 9.8 gives you exactly 3.92. So you've either got this version or this version. So the acceleration is 3.92 meters per second. Okay, so I hope that's given you an idea on that question. It is long. Most of the time is spent just establishing the diagram, I feel, but do take care over that. All right?